Okay, I'll have to check. Let's check the stream working. Am I audible here? Okay, I'll have to check. Wow, that's a lot of latency, but okay. Yeah, cool, it is working. Let's check. That is stream working. Am I audible here? Okay, I'll have to check. I'm still an open. Wow, that's a lot of latency, but okay. Yeah, cool, it is working. Let's check. So I can enter that is here. Am I audible here? Let's check this out. Okay. Okay. So what are we doing today? What are we going today? So, as those who must have followed the previous stream, you might be aware of the research paper we wrote, right? We wrote a research paper from scratch. It must be here somewhere. Is it here? No. Okay, let's quickly find it. Yeah. So see, in the previous stream where we wrote a research paper from scratch, we wrote this research paper which mainly talks about the limitations of backpropagation, where we train all of the neural network layers together. And in this paper, we wrote a different type of learning algorithm where we used backpropagation itself, but we trained each layer greedily, right? That was the difference. So this is a general neural network. This is how it works. The last layer learns losses, then it gradient passes to this layer, then this layer, then this layer, and these all of these layers are optimized at the same time. Okay, one iteration moves the weight of each of these layers in the right direction to change the overall loss function. Now, what we proposed was, instead of using this, which can cause overfitting and make a more complex mathematical function, and we are not able to interpret each of the layers individually in a proper fashion because each of the layers results are obtained at the same time. There is no loss per layer, so we can't understand the bottleneck information bottleneck correctly, right? So those are the issues in it. And then we propose the network that, okay, we'll use a individual dense layer for each of the layers and then train each of these layers individually and freeze the layer after it has learned, so that it acts as a fixed mathematical function that then forces this layer to learn according with respect to the parameters learned by this layer. So what happens is each layer gets the chance to meet the final loss functions in a closer fashion rather than backpropagating through all of these functions, and this layer doesn't get to understand what the last thing we are trying to obtain is. Rather, it just obtains its interpretations from the second layer, and the second layer obtains them from third layer in a traditional network. So that's what we changed earlier, right? If I'm able to make you understand this, I don't think I was very good in explaining, but okay, that's what we did. So the benefit we showed with the help of these graphs, or this is how a normal neural network graph looks like. But we said if we are breaking them into layer wise training, so the graph will tell us the loss for each layer, so we can clearly see how each layer is saturating, what weight each layer is saturating into, which makes it easier for us to identify which layer might be causing a bottleneck and how many layers we need to use. So overall, it helps us design better architecture for our neural network in a simpler manner. That's what it does, right? So this was the whole paper. This is what we talked about. The interpretability of our network was better than the previous. The accuracy and time taken by our network was even better than the traditional network. So this is all of what we did. And yeah, so this goes to show what preliminary work you have to do in a research paper. We also searched a bit of the previous papers that have been written in this context, and then we uh, found some references. We wrote about them. We got to learn that this type of ideas have been followed earlier too. I thought I have this idea from scratch, but don't you know, like there was a paper on it from past itself, so it was not just my idea. So that happens in research paper or anything, any idea you think that might have been thought by someone else before you. This is the world has a population of 7 billion people, so you can't really expect to have that unique of an idea. So that's fine, we can improve on the ideas anyway, so that's nothing to be demotivated of. So yeah, so that is all of what we did. Now, what are we doing in this stream then? Then everything was over. We wrote the paper, we got the idea, we coded the idea, we did experiments on the idea, we got the experiment results on the idea. The experimental results showed that our idea works better. So what is left? Why is the paper still not published? So when you are publishing a paper, this is not all the things that you need. You need more concrete proofs to publish a research paper. So how do we obtain a more concrete proof? Now, okay, if some of you might not know this, but actually I'm a mechanical engineering student. So the first thing that comes to my mind is make an application based on the network that we made related to mechanical engineering, where we can easily showcase that our idea did improve the previously proposed ideas. Right. So I found this data set on Kaggle itself. Where is it? There is the data set, the metal surface defect data set. So what is this data set? This data set has 1800 grayscale images, 300 for each 6 different categories of surface defects. So this is the data set. There are various images in the data set. So what it basically is there are 200 by 200 sized images, and these images are of metal surface of different defected surfaces. So right, so the metal surface with scratches looks somewhat like this. The metal surface that has rolled defects looks something like this. Okay, so what we need to do is we need to make a neural network, most probably a convolutional neural network that can um, segment these images, that can help us identify the various classes of images. Now, what we have to basically do then? We have to make a image multi-class classification model. Now, how do we make a multi-class classification model? We use convolutional neural network with a softmax layer in the end and use uh, cross entropy laws in the end to train it, right? So that's what we do. So I was going through some research papers on classification of surface defects, right? And we have found I was particularly looking at the research papers that use this particular data set, right? Because I'll be using the same data set. So I found that there was a paper proposed that used this neural network. So I was like, okay, we already have a neural network here, right? Which uses very basic ideas, and now there is something in this layer where they, something in this paper where they use uh, sparse auto encoding uh, for estimating the weights. So as most of you would know, if you are already aware of neural networks, when we are training a neural network, we initialize the weights randomly, right? That happens most of the times. But sometimes, to reach a global minimum in the loss values, we use another kind of initialization where we use another network or some kind of experts insight into our training data, so that we can initialize the weights in a better manner that gives us more chances to reach the global minimum. So in this paper they use such techniques. They talk about a technique with sparse autoencoders. So what is sparse autoencoder? Sparse autoencoder is basically a simple autoencoder. Here you go. It just uses L1 regularization so that the weights aren't initialized to a very high value. And this is a basic autoencoder. First is are few encoding layers, then there are decoding layers. So if you are aware of autoencoders, you must be aware of this. So that's what they use. Now we are not going to dwell into all of this because we don't want to initialize, we don't want to necessarily reach a minimum loss. We don't necessarily want to make a network that fits to this data perfectly, but instead we just want to prove that our training method is better than the normal traditional training method. And the losses they obtained, they have a graph for it. They have a graph where they show what are the training losses they obtained when they use, here you go, when they use random initialization. What are the training loss they were able to obtain? The error rate, right? So we can use this error rate that is available to us and compare our learning method to their random initialization error rate, keeping all the other hyperparameters same, to see if our model actually reaches a better error rate than theirs by simply changing the training algorithm. So what this will prove is our training technique actually gives more chances to reach global minimum without the use of any special techniques. Now we'll have to use all the other techniques mentioned in this paper. They have used various data augmentation techniques. They have used what were the number of epochs they were training for, what were the hyperparameters. All of that we will have to keep the same. So we'll have to go through this paper over and over again. So I guess while following this along, we'll also get to learn how to reconstruct a paper, right? So that is also something we will be learning here, right? Okay. So first of all, let's get our data in a Colab notebook and let's pre-process the data initially. That's the first thing we should do. Okay. Okay, stream is working, I guess. Okay. Yeah. Let's open Colab. I was looking at something that how can you mount your drive directly to Colab so that because you know the issues with Colab where you have to again and again upload the data if your runtime gets slow. It's just annoying. So we'll try to take care of it. So maybe I can, but doing it with a GPU is better, right? In my Mac, I'll be not be able to use a GPU. Yeah, training with a GPU is better. So let's go on with this. Again, let's try to pre-process the data first. Let's try to bring our data. So before pre-processing, let's decide some things. Okay, first of all, let's see if we can even bring our data to Colab. What runtime is it giving me? Oh, it's TPU, not TPU, GPU. Okay. They are not gonna give me a TPU for free that easily. Okay, I hope you will not ask for a password. Okay, come on. Okay, so there's something around this. Hmm. No such file or directory is right there. Should I write it without space? Without. Ah, okay. Okay, cool. So what should we do? Should we do it manually or should we do it with the help of? So let me tell you what we are trying to do. We are trying to make a data set with images on one side, right? And our what to call this? The category of error on one side. So okay, so these are the 6 types of errors. So let's try to decide something first. So what we are gonna do is we will call crazing as one, inclusion as two. Let's start with zero. Like all good programmers, patches as two, fitted, he rolled four, patches as five. Right. So this is something we have to keep in mind. Maybe we can even write down it in a markdown rather than this. That would be easier to go through. Necessary assumptions. Yeah, it's fine to call it that. Ah, this is so annoying. I hate markdown for this specific reason. Uh, okay, now it should be fine. Alex, we are doing that much. I don't know why I'm wasting everyone's time. Oh god, this will still not work. It does work, right? Yeah, okay, now it works. It needs double. Hmm. Okay, good. So these are the initial assumptions. So what we are gonna do is we're gonna read these files folder by folder, right? How do I wanna read this? There are two ways to read it. Either, okay, so what can I do is either I can directly make a numpy array, right? Where I store the images, flattened images, or there the simpler way is I store the location of the image, right? And with that, I store what category it belongs to. And when I'll be going through my network, but it will not allow me to pre-process the image. Okay. Let's do one thing. Let's go folder by this. I'm not really sure how to pre-process this. That's ridiculous. Okay, so for fn was total is dir. ना इस dir को हम लोग लिस्ट करा लेंगे import os है ना तो let's store it. How do I store all of this in a data? Import torch. Import torch. By that's all of it will be needing. There is a way to do this directly in Torch, right? There is a way to directly read a folder of images, classify them. I think there is. How to read an image classification dataset in Torch. Read an image. Yeah, this is it, right? Hmm. This is unnecessary. Dataset is equal to dataset.image folder. Okay, what it gives us, transforms. I know what transforms is. So what it gives us, what are the labels? Get this. Will I have to read slow? Okay, cat.data, folder name cat and dog. Those are the two folders, right? Those are the two folders. Now I imported Torch. In Torch using the datasets, I imported image folders. Image folder expects the files and directory to be considered like so. Root dog. Okay, that has been done. Where each class has its own directory, cat and dog for images. The images are then labeled with class taken from the directory name. So here the image 123 would be loaded with the class label cat. You can download the dataset already structured in the form like this. I also split it in training and test set. Yeah. But I forgot a lot of this. I have not practiced it in a long time. And I've actually forgot a lot of this. Hey, okay, let's try to do it this way. Not use it. What we're gonna do is, where was it? Post is in import dataset and transform. And nothing could go wrong. We'll figure this out. Oh, make some transforms. And those import transforms. So, okay. So we'll do transforms.compose, right? Hmm. Transforms.compose. Oh god. Oh, there was one normalized. We need this. Has he used it? But two tensor is all we need, right? And dot resize. Resize, I think in the paper they resize it to. Wait a second. Okay. Okay, no more distractions. No more distraction. Take it to vibrate for now. So, okay. Transforms dot resize. That's what we'll be needing. We'll be needing transforms dot to tensor. Right. And there was one more. Transform dot normalize. That exists. Yeah, transform dot normalize does exist, right? The function takes to argument the mean and the standard deviation of the data set. Mean is one, standard deviation is Minus 0 standard deviation is 1. Why would this keep both of these 0? And does it necessarily need it, or can it take it by default? Not sure. Mean standard deviation. Okay, mean is 0, standard deviation is 1. Basic. So let's call in the data set. Data set is equal to data sets dot image folder. Why am I giving it like this? Okay, now let's try to print our data set by loading it first. I remember this. Let's run these much lines. Let's see if we haven't made an error first. There must not be an error there. Two positional arguments, 4 were given. Oh, I need to make a list of. Now it works. Okay, so print next iter data loader. That's how we used to call it, as much as I can remember. That's taking awfully lot of time. Okay, so it is like this, right? I don't understand. Where is the class? Let's store it somewhere. Because we are gonna play around with this. Understand this first. I'm sorry. I don't think this should have been happening. But it's better to take things slow, understand the basics first, understand what you are working with, and then we can easily focus on the AI part. Let's get this done here. This is the part I'm not good with anyway. So, there we go. This is what we have. Data.shape. Let's look at the shape. Ah, doing. Data is a list. Data. Shape. 32, 3, 40, 40. So first of all, these are grayscale images. So I need one more transforms dot grayscale. Yeah, that is also necessary then. But other than that, what I'm confused about is where are my labels? There are no labels, right? He has not stored my labels. What was he talking about? How did he got labels? I'm just common labels in data loader. How did I do it? Do we have to give something? Tell it. I think he did. Yeah, this all makes sense, but how do we get the labels? Okay, let's try to write it in this way then. The shape seems right, but this also makes sense. Okay, let's write another code for it. And let's run this first again because we have grayscale now. It should make all the processes faster. Yeah, okay. So we have got a lot of things solved. Now what we should do is put image comma label and image. Okay, we have this. Now we are gonna call matplotlib. Hmm. There's another way to do this. Yeah, we stop. Okay, so we have the dataset loaded. It is working. Good. Let's make it in a cleaner way for now. Count is equal to 0. Take equal to 4,8. What is that? Okay, get it. Get it. I think I can do this. Okay, where is it? AXS. Right. Let's do this. Let's direction तो ऐसे करके हो जाएगा. We don't want one direction. 4,8. We want all is equal to. I can write this in a much better way though. You know what we should do? Image set and label set now. You do no. Okay. Nd array. Oh, sorry. Object is not callable. Yeah, how did we do this? X is not set title. Let's acknowledge a bit. Now it works. Now it works. Why does it like this? Oh, okay. Okay, that's weird. Now it does work, but I have one problem with this. It looks annoying. So first of all, I think I remember this. You have to say access dot. I think this was it. Yep, here we go. Good. Now we have a clean data set of images and now we are able to display it. Displaying it is a big deal, according to me, because if you are able to display the data set in the way you like, it means you have understood the data set enough. So let's see. Okay, so now this doesn't work as we are not doing it manually anymore. So we'll have to see how this has done it. So my assumption would be it should be the same as this. Why? Because it might be taking it in the alphabetical order, and according to alphabetical order, this must be correct. But I am not sure. So how do I verify this? That's difficult. That is actually very. How do I figure that out? First of all, let's take all of the import statements somewhere. Otherwise, we'll lose track of them. Important not to do so. Hmm, let's try one more thing though. These are the negatives of each other. So I think I want to see how our data set suits. Where was the data set? Let's see. Let's go for any scratches image. Okay. So the scratches are from white and the whole of the image is gray. Yeah, I think that's the correct one then. This all belongs to five. Five must be scratches. Okay, that assumption is correct. Now let's see four. How does four look in general? This is just, what we are doing right now is just like a sanity check so that we don't make any big mistakes later on. So we are just, checking the data slowly, going with it slow, understanding if we have done everything correctly, so that we can move on. So four, it is a bit confusing. It does look like that these kind of dots are there in four. Let's check something else. Maybe we can come to that with the process of elimination. So zero, or maybe something like three. Okay, three has this gradient kind of effect, right? All of the threes. So let's see. Three must be, according to our assumption, must be fitted. Okay, it does have the gradient effect. So I think we are right. Right. So crazing, how does crazing look? Crazing looks like old concrete buildings, old paint. What does zero look like? Yeah, it does look like that a bit. Maybe we should check one, two, just to be sure. Inclusion has this effect. Yeah, this must be right, right? Because let's check the patching again. Patching is also a very giveaway kind of a thing. So it has these very dark patches, right? So let's see, do we have them in the two? Yep. So this assumption stands correct. Takes them in alphabetical order. And these are the classes. So we now have our data set. So now we can train our data set, train on our data set. So let's try to import torch.nn as an okay. Let's keep that here too. Now one more thing that we have to do is hmm, let's make our model now. So let's make our model. What does the model look like? Let's try to be simple first and let's try to train copy their model and try to train on it. That's the simplest thing we can do. Then we'll have to also take care of the hyperparameters. So yeah, we have to do first training hyperparameters and all that stuff. I've made the batch size to be 32 for now, but I'm not sure what batch size they are using. I'm sure about the resizing, I'm sure about the tensor, I'm sure about the grayscale, I'm sure about the normalization. Let's see. Is anyone here? Okay, one that must be me. Oh shit. Oh no. Is the data lost? Please don't tell me. Oh no. Okay, it is all here. Okay. What runtime are you giving me? Good, 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 good. Oh, will I have to give it every time? It's fine. It's still faster than uploading into Google Colab itself. Drive the data is stored at least. I don't have to upload it over and over again. Uh, what are these even for anymore? Okay, now we get an error. Oh, wow, we really did that, huh? Oh, no. Oh, oh, wow. Oh, that's so long. Are you kidding me with that? That's ridiculous. Wow. Okay, so we have traced our way back. Now, let's start making the model. Do we have to attend? Okay. So what we are gonna do is now we are gonna make this same model here. So we have resized our images into 40 by 42. We also have a single layer because of the grayscale images. Now we used to need to use 5 by 5 kernel. Then we used to do max pooling. I think I read the paper correctly. They use max pooling and all of this stuff. So let's just quickly make this. Let's just quickly make this class model. Then classify. Do we need any input for the model? No. Hmm. Input channels. There are two ways to do this. Okay. So they must be always using the same activation. So okay, the paper had something very interesting. Or not interesting. I just found it no. I don't know. I must be not updated correctly, but they, they just used linear activation. Like it is like having no activation at all. And they say this gives them the best result. I don't get it. I really don't get it. This is just like using no activation layer at all. But I guess we'll have to follow this, so let's live with it. Okay. 20 feature maps, 20, 50, 15. Where were we? For the initial layer, we are gonna convert a 40 by 40 layer into a 36 by 36 with the help of a 5 by 5 kernel size. So the kernel size is 5. And the input channels are gonna be 1. And the output channels are gonna be 20. And the kernel size is 25. Right, that is the first convolution here. Now let's have self dot max pool. Max pool in 2D. तो क्या क्या चाहिए होगा kernel size. Right, we're gonna half that, right? So here, okay, we'll do that later. So self dot contour is equal to फिर दोबारा मैक्स पूल होगा, so I'm not writing that again. मैक्स पूल होने के बाद फिर 4 by 4 कर्नल साइज से पास करा. Okay. And 400 feature maps, so 50 to 400. And did I miss a step? This is the first convolution. This is the second convolution where we're going to 50 feature maps के ऊपर we need a convolution, right? Why am I getting confused? Okay, so this is the first convolution layer, after which we apply a max pooling layer, after which we apply a convolution layer that converts it to 50. That's the mistake. And with a kernel size of 5. Now we apply another subsampling layer that makes it 7 by 7. Right. And after that, we apply a 4 by 4 convolution which takes the 50 to 200, 400. 50 to 400. Self.conv 3 and then the conv 2d 50 to 400 with a kernel size of 4 this time. And this, we flatten this, right? Because 4 into 4 is 16. 16 into 400 would be 6400. So this is just flattening the layer. And after flattening, we use a dense layer with a softmax activation that converts into 8 units. Now wait a minute. Why are we using 8 units? We only have 6 classes to divide from. But we are here using 8 units. Why would that be? Why would that be the case? We'll have to read the paper. Can this be a... How can they make this mistake? This cannot be a mistake. I don't get it. Wait a minute. They say the confidence of each class, but the dataset we are using only has six different classes. How are they getting at eight different classes? The dataset is exactly the same. Thus, their dataset has more classes than mine. They must have written it somewhere, right? There's the dataset section. Pro pixel image directly. Yes, that's correct. Yes. Okay, convolutions. I understand how computations work. Experiment dataset of surface defects. Yeah, there you go. Grazing folding? Oh no, I don't have the same dataset. What the hell? We also have 300 grayscale images per class, but we don't have the folding and rolling in scale. We have rolling, rolled in scale, scratch, fitted surface, patch, grazing. We have grazing, we have inclusion, we have patch. 1, 2, 3, 4, 5, 6, 7. It still makes up for 7. They also have a no surface defect based image. Okay, here is their dataset. Let's look at the references. Let's find their dataset. Yeah, our dataset is a bit different. That's annoying. They said they have an NEU dataset, right? That's it. NEU metal surface defect dataset. Yeah, this is the one I'm using. It only has six classes. There must be another one. The similar datasets. Wow, this is not similar at all. It's just don't keep bringing me to the same page. And this looks bigger. Okay, this is something completely different. Yeah, show me the datasets. This is a different dataset. Different types of defects. I didn't even know about this. No, but I need two more classes to prove myself. Okay, this is getting funny. I need to use the exact same dataset if I have to prove myself worthy. But I don't seem to be able to find the same datasets. We'll have to go through the references very slowly now. Most robust method based on computing. cannot share the data set. In name will get it. Not share the. Ah, this is annoying. This is just annoying. Can't find a link to the data set. Proving it here help. It's layers. Can easily argue, right? They can easily argue that I am classifying on 6 classes. They had classified on 8 classes, so therefore their accuracy was not as good as mine. I would not be able to prove exactly how my accuracy is better unless and okay. So what will I have to do is okay, it's fine. It's fine. Let's work with this. Okay. We need expert guidance into this, so we'll have to. I'm not giving you away my GPU. So what we'll have to do is we need some expert guidance into this. So we'll do this experiment today right here. And what we'll do is we'll train it to normal training, their same exact network. Then we'll train by our method, their network on the same data set that we are presenting here. If we have used here that is available to us with 6 different classes, not 8. And we'll compare the results according to them, and I think that should suffice as a proof. At least it's what that looks like to me, but I'm not sure if they will be happy with that proof. So I'll have to come back to this paper again, I guess, but that's fine. That's fine. That's good. I love this paper. I love the idea I have presented here. I can keep coming back to it over and over again. Let's see where was the paper you were reading. Yeah. So have we made our model now? Yeah, we just need to flatten it, and after flattening, we need to use a linear layer with a softmax activation from 6. Okay, so we don't need to really find it. Self dot dense is equal to nn dot on 2d. Like nn dot linear. Now I will find it from 6400 to 6. Self dot final activation. You know why we are doing one? Because there are 36 samples. There are 32. There are the batch size is 32, right? We are using the 32 batch size in the first time. That's the zero dimension, right? Those are the number of rows. There are 6 features in each. So by telling it that we want to use the convolution, that we need to use the softmax in first dimension, we're just telling it that it needs to apply the softmax like this, right? Let's see. Let's see if we can visually see it. Softmax dim mean. So see, this is dim 0, this is dim 1, this is dim 2. 0, as you know, 0 is our batch size, and 1 is this. We are telling it to keep doing the softmax in these layers for the 30 classes. Okay. It would make more sense. You would easily be able to see it. Let's see if this can explain it. So softmax is function is equal to n in the softmax dimension 1. So output is equal to softmax function of input. They have not shown us the input. That doesn't help. Um, Let me see if I can explain it to you somehow. Yeah, so you can see it here, right? You can see it here. So they applied on the zeroth dimension. So it got applied here. So if we have two dimensions where, right? So if we implement in the zeroth dimension, that will implement it like this. So it will take softmax of those batches. That's not what we want. We want the softmax to be applied on the different classes of the same batch. So that's all we are doing with this. Okay, all we are doing. I hope that makes sense. That's the final activation, and those are all the layers we need. Step forward. One more thing that I'll add maybe is self.activation. I know they have used linear, as ridiculous as it is, but I think I'll just apply it anyway. Identity, right? I think I remember that. So x is equal to लास्ट के बाद करना था क्या? कौन 3 है कौन सी? ये है क्या? यही है, इसके बाद नहीं करना है मैक्स। Right. And let's add an activation in between all of this. So convolution layer, pooling layer, activation layer. That's how it goes, right? So after pooling. right? All of this is done. Now we have copied their whole function. Let's see. Here we should have a size of 1 cross 4, 40 cross 40. Then, I mean, x then it come into this. After this, it will become 1 into 36. 36. After this, it will become 1 into 18 into 18. This will remain the same. 18. After this, it will become 1 into 14 to 14. After this, it will become 1 into 7 into 7. This will remain the same. Here it will become 1 into 4 into 4. And here it will also remain the same. Here a second, why am I keep writing 1? So after this, it will become 20. It will remain 20. Remain 20. Here it should remain 20. After this, it should become 50. It should remain 50. It become 400. 400. Now it should be 6400. This should be 6. The final size should be 6. Let's make a test for this. Test classifier is equal to find. ये होगी 1 command 50 comma. Okay, कहाँ गलती हो गई मुझसे? I don't think it's not callable, he said. The hell? Interesting. We have got an error. When we flattened it, Everything seems to be working fine now. Yeah, so basically, instead of using flatten, in flatten, some of the times what happens is it flattens the layer from one dimension only. It assumes the first dimension to be our batch size, and that's why it sometimes causes error. So instead of using that, we can use this. Now, why am I doing it like this? So it is safer to do it like this because if we have multiple, I don't think it will bring any difference. Like that is never gonna change. So yeah, we can just say 1 by minus 1. That's safe to say. Now we can pass multiple classes too, and I think this should work fine. What the hell do I have to? Oh no, 4 comma 1. And now it is giving errors. That's why I was saying minus 1 and 6400. Yeah, this works, right? So this helps us to take care of the batch. Right, so if we wanna have multiple batches, it should work just fine. Get 6 outputs, and the sum of them um, I can look now. अरे बोल तो करो. Don't take at least one position argument 0 but you know. All of them comes out to be 1. So the softmax is also working perfectly because when we are summing those 6 values, it is coming out to be 1. Otherwise, if it would have been like this should not have sum to 1. So, yep, everything is going on right. We are getting the correct output. The, the 8 batches. I don't think there might be a mistake there anymore. I'm still scared of this thing. No, it doesn't feel right. How to use flatten? Source dot flatten input starting ending. Start dim. So instead of using this, I don't know, I'm too skeptical of this. What, but I don't want to. Will this work? This works. So I'm trusting this more than that. One more thing, let's check it out again. Hmm. Yeah. Now we have built our model. Now we have copied the model represented in this paper. We have built it to our own model, and we can easily run through it with any batch size we want. So now let's read through the hyperparameters used in this paper so that we can copy that too and train our model on these 6 classes that we have in our training data. Time is it? How much time have we been streaming from? This is not updated, is it? Okay, now it is updated. Now the chat is not showing up. Okay, I'm new to this. Please wait. Okay, someone asked me what is your research paper about. So basically, let me show it to you. I You must have asked it way earlier, bro. I'm really sorry. Too much focused. Okay, it doesn't show the time. Okay. So basically, this research paper is about well, if you know about backpropagation in neural networks. So basically, in traditional backpropagation, what happens is we train each of the layers at the same time in the same iterations. So what this paper is about is, what if instead of training all the layers from a single loss functions like with this here, so what happens in this type of training is that the last layer is the only one that gets a chance to be introduced to the final loss function or the final loss that we are training for. And all of these layers are trained according to their next layers, right? So this layer has the least information about what the final layer actually is. Whatever it knows about the neural network is based on what the second layer tells it, and whatever the second layer known is based on the third layer, whatever the third layer knows is based on the fourth layer. So instead of using these, instead we have proposed a network training method where we use a dense layer, different dense layers for each of the layers, which we can discard after training. And what we do is we train the first layer with the help of this dense layer directly on the loss function. Once this layer is trained to a satisfactory result, we freeze this layer, then we introduce the new layer, then we train that layer, freezing this layer, and then when the second layer is trained, we freeze that and introduce a new layer. So what I'm proposing is that using this method would be better than the traditional training methods available. Why? Because training like this would help us prevent overfitting. One, because the second layer would only be introduced if we are not happy enough with the first results data set, and we can build the architecture in a more constructive, in a more knowledgeable way where the interpretability of the AI increases. And also the mathematical functions are fixed. If we consider neural network as a function approximator, by using and training a single layer at a time, what we are doing is we are basically freezing a layer, we are freezing a mathematical function, and we are only introducing more complexities to the function based on what the first function has learned. So basically, we somehow prevent overfitting. We help decrease the training time because only one layer has to be trained at a time, and we are also increasing the chances of reaching the maximum optimum. Now in a previous stream I did all of this, Um, and all of those that this paper has been written on the stream and explained thoroughly how we experimented it, what the experiment showed us. These were the graphs. So one more thing I wanted to show is that the graphs are much more interpretable when we use layer wise training. So see, this is a basic traditional neural network training graph. It doesn't teach you much about what the layer is doing, like if a layer is causing an information bottleneck or if a layer is decreasing the accuracy. You don't know about layer wise layer training. But when we use this technique that we are using here, we get to know the graph as per each layer. So what happens is, if this layer had saturated way above the other two layers, we would have instantly interpreted that this layer, the second layer, is causing errors in the network, it causing an information bottleneck, and we have to somehow change that layer. So the interpretability has been heavily increased by using this method. Other than that, these were the training time results, and there was one more interesting result that I wanted to show. So basically, what happens is, when we train in the traditional form, so for a classification task, it is the input image is this, and the layer 1 features look somewhat like this. So you can easily interpret there is a car, there are just different shadings of it. It is trying to detect different edges in it and all. But when you come to the second layer, it is totally uninterpretable by human for a traditional neural network, right? You can't see a car in it anymore. You can't understand any edges, what they represent. This is just some jumble, something, some trash, not exactly trash, it's trash to humanize, but some computational 0 1 binary trash that the computer has been interpret so that it can classify the images. But if we use the layer wise training, you can see how much more interpretable that is. This is as 50%, this is layer wise training in a 50% degree. But if we completely train it layer by layer, you will be able to see that this is the first layer training parameters. These are the different shades of forces. This is exactly the same as a traditional neural network. But when we come to the layer 2 features, they are much more interpretable. You can even see that there was a person sitting on the above the horse. So one of the images does not have that person sitting on the horse. So it is able to take the horse out of the picture completely, focus on the horse itself. This is much more interpretable by human eyes, and this seems like a much more insightful and thoughtful interpretations made from the input layer to reach the conclusion of classification. So that was my whole point in the previous videos. And now in this video, what exactly we are trying to do is that we have already done this much, but in this video, what we are trying to do is we are trying to prove the applicability of this training technique by using a previous research paper on metal surface classification using the NEU dataset. And what we are doing is we are using their same neural network and training them once by traditional network training and once by our proposed method, the greedy layer wise training. And what we are trying to see is what are the differences in the accuracy and training time achieved when we train it by our training method, and what happens when we train their network using the traditional training method. So that's what we are trying to do. So till now we have just written a code for basic data processing, and now we have finally completed writing the code for CNN classifier. So we have copied their exact classifier model. I might even be able to show you this. Okay, so let's see the visual diagram of it. Are you interested in that? Should we see how the network looks visually? What do you say? If anyone is here. Okay, let's do it. Anyways, we have to do it, right? So, how to apply those one. So I had this method, made the code, made the network, print network, visualize for the single function rule. Yeah, this one was bad. I hated it. There was a third method. Yeah. What is X? Let's just do it. X must be the input, I assume. Input names. It metal surface defect images. Output names. Confidence in each class. Okay, this is it. Mm, This has not happened to me before. This is how we used to do it, right? Mm, mm. Oh, okay. Oh my God. I didn't even notice that. How is it? That's why it was not working. That's why it was saying it is not callable. Oh my God, I just didn't notice it. Wow, I don't know how it worked till there too. That's what you do, right? All right. That- That's not how you do it. Rest everything is working. Okay. Why is this not working? Leave this. This used to work. It must be a silly error. That's a weird error to be. Input comma लगाऊं first of all. Put names में there should be a list. No, put names में there should be a list. I would only assume. Hmm. Wow, you finally get that. कभी रंग रूप देखता नहीं. Okay. Now it should work. It did work. Now we must have an ONNX file here. Good. We'll download this file. The desktop. Save this file. I will open this file. Yep, there you go. It's a very bad file. Just like that. Now it works. So here you go. Now you have a visualization for it. Now everything is visible, right? So wait a minute, this looks weird. Oh, okay. That's just the dense layer. But okay, 8.6, right? So we flatten it. We know the dimensions. So no, we can't. I think it must be right. Let's do it for goodness sake. पहले है 8 400 400 8686. Yep, that's how it should have been. Okay, so now we have a working model. Now let's make a training loop. Do they have the graph for both? Yeah, just use the training loss. I think it would be fine for us to also use the training loss. Why not? Let's have a def train loss. Okay.